So specifically, we are going to consider the effect of temperature and non-isothermal reactor behavior on reversible reactions. And for this example, we are going to consider the isomerization reaction where pure A, so initially I have pure A and it's converted reversibly to B. Regardless of the type of reactor, this is the shape of the rate equation in that case. So in addition to the concentration effect on the rate, which I can now express in terms of the conversion of my reactant A, because I knew my initial CB naught is 0 and I was given a specific CA naught, there are two temperature dependent parameters in this rate equation. Of course, the first one is our Arrhenius temperature dependence of our rate constant. This parameter will always experience an exponential increase with temperature. The activation energy will always be positive. I do not get a negative activation energy. So in that typical Arrhenius plot, if I present ln K versus 1 over temperature, the slope will be negative because E will always be positive. Increase in temperature, increase in that rate constant, and it's an exponential increase with temperature. For my equilibrium constant, I am going to use the Van Hoff approximation for its temperature dependence. You can go and revise its derivation in Smith, Van Ness and Abbott in chapter 13. However, it relies on the assumption that del H and del S of the reaction is not a function of temperature. But here in this subject, we are just going to use it. Once again, we can see that there's an exponential change in my Kc as a function of temperature. However, the direction of this change depends on this parameter, the del H of the reaction. For an endothermic reaction, that slope is going to be negative, ln of Kc versus 1 over temperature, and I will see an increase in K with an increase in temperature. For an exothermic reaction, I've got a negative multiplied by a negative value, and I'm going to have a positive slope, ln Kc versus 1 over temperature, and I will see a decrease in Kc as I increase my temperature. A reminder that we specifically use the Kc to remind ourselves that when we calculate this parameter in terms of the concentration in my reactor or in my system, Kc says you need to calculate the concentrations at equilibrium multiplied the concentrations at equilibrium raised to their stoichiometric coefficient as they participate in that reaction. So for our specific reaction, it will be the concentration of B at equilibrium. Its stoichiometric coefficient is 1, and for A, the stoichiometric coefficient is -1. And I can express those two concentrations as a function of the conversion of A, and I end up proving that my Kc in this constant is an equation that is a function of my conversion of component A under equilibrium conditions. So I can derive this equation from two possible ends. I can say, right, let's make the equilibrium conversion of component A the subject of that equation, and we realize that it is a function of a temperature dependent parameter, and of course in the place of that temperature dependent parameter we need to substitute our whole Van Hoff equation. Or we can also derive this equation by realizing that if the rate is equal to 0, rate of our equation must be equal to 0 under equilibrium conditions, and we can once again derive an equation for the equilibrium conversion as a function of our equilibrium constant. So if I substitute the Van Hoff equation into the Kc as a function of temperature, I can actually calculate the equilibrium conversion as a function of temperature Depending on whether it's an exothermic reaction, it's going to follow this shape. It makes sense. At a higher temperature, I will have a lower equilibrium conversion. And then for an endothermic reaction at a higher temperature, I will have a higher conversion. So this plot, both the red line and the blue line, is a combination of this X equilibrium and our Van 't Hoff equation. So now we specifically want to see the effect of a combination of this temperature dependence, temperature and composition dependence of my rate equation in adiabatic reactors, adiabatic non-isothermal reactors. So in an adiabatic reactor, if you consider the previous slides, for this single reaction, we can come up with a linear algebraic equation for my energy balance where I have a linear relationship of how temperature changes as a function of X. So, and this can be derived either for a CSTR or a PFR or a PBR because we assume that del H of the reaction is independent of temperature, and we can obtain this linear algebraic equation even for a PFR reactor that represents my energy balance. So before you start designing a plant, it's always a good idea to make sure that it's actually worthwhile in terms of the thermodynamics to actually say what is the limiting conversion, what is the maximum amount that I can actually produce, and that if I could have an infinitely large reactor regardless of whether it's a CSTR or a PBR will be defined by that position where my energy balance intersects my equilibrium line. So how to solve that? No questions asked about the type of reactor, but the two equations you must solve simultaneously is your adiabatic energy balance and your equilibrium X. So that will give me the temperature where my conversion has reached equilibrium, and it will also give me the corresponding equilibrium X. Two equations, two unknowns to solve simultaneously. But if we now want to design our reactors to achieve a certain conversion that is within the limits of possibility given our energy balance and our equilibrium limitations, we need to evaluate the effect of conversion on my rate. And what we must realize is as I have a specific X value, let's say X changes between 0 and 1 once again, I can calculate the resultant temperature. And if I have the resultant temperature, I already know my composition for each X. I can now calculate the temperature and substitute that temperature in my Arrhenius equation and my Van 't Hoff equation so that I can get a rate for each X. And this is now presented over here as the Levenspiel plot, where I have -1 over the rate as a function of the conversion of my reactant A. So what I will see here is that initially there is an increase in the rate. The increase is due to the fact that, yes, I have no X, so I have no product that can react here in the reverse direction. So initially the temperature increase, exponential temperature effect dominate as this K increases exponentially, and it will go to a maximum value, and then the rate is going to decrease for two reasons, because I have no reactant left and I have some product that can react in the reverse direction, and this rate constant is also going to increase with an increase in temperature. The shape of this figure will depend on parameters such as my heat of reaction. So how does it look like this, or does it follow an even flatter line and then a sudden drop? That will depend on my heat of reaction and my activation energy and their relative size respectively. If I have an endothermic reversible reaction, I do not observe this maximum, this initial increase in the rate, because as I increase conversion, there's only going to be a decrease in the temperature, so my concentration of the reactant decreases, my rate constant decreases because I have a decrease in temperature, and I will just see a decrease in the rate going to that asymptotic value where I reach my equilibrium conversion and the rate goes to 0. So when you plot a Levenspiel plot, for a reversible reaction and you don't know where that equilibrium conversion is. It is always a danger that you will get this warning from Python wherever you do that calculation. When this rate goes to 0 at equilibrium, it's going to complain that you want to divide by a 0 and it's just going to bomb out and give you a pink screen. So it is actually for reversible reactions easier or safer if you choose an x value that goes from 0 to 1 to plot the rate versus x and not 1 over the rate. So you will observe the same behavior. You will see an increase in the rate. You will see the maximum in the rate. You will see that the rate goes to 0 at that asymptote value. And then it seems as if the rate goes into negative territory. That's the reverse reaction. Of course, that is not going to occur in your reactor unless you disturb the conditions in the reactor using some external conditions like removing some of your product in another side reaction or changing your temperature by having some heat transfer in that reactor. So your reaction will stop where this rate goes to 0, and that is not where x is 1, but that is at that equilibrium conversion in your reactor. The Lebensspiel plot is handy, of course, because it gives us a graphical idea of when we size reactors to obtain the minimum amount of catalyst or the minimum volume. We would first, especially for exothermic reversible reactions, target the point where the rate is a maximum and operate. Remember, a CSTR operates at a specific state, so it will operate at that rate, and at that maximum rate I will target a CSTR. I can calculate the mass of catalyst, in this case in my CSTR, by considering that little area that I have here, which is the X at that maximum rate point, divided by that maximum rate. So it's multiplied by -1 over R, and just look at your mole balance to see that you still need an FA0 in order to calculate the amount of catalyst in your CSTR. So if I now want to target a higher overall conversion, I would now follow that with a PFR or a PBR in this case, operated in series with my CSTR. And of course here I have to integrate and consider all the different rates as the rate is changing along the length of my reactor, and my integration boundaries will be from X at the inlet, which is the CSTR outlet, going to the desired conversion that I want in my PBR reactor. For an endothermic reactor, packed bed reactor will always be best because I can follow the rate as it decreases instead of having to operate at that low rate at the desired conversion, and therefore having to have this whole area that would be required for my CSTR, of course, multiplied by that FA0.